Given two sets A and B, we know that the number of elements in A union B is the number of elements in A plus the number of elements in B minus the number of elements in their intersection. Could we extend this formula to a situation where we have three sets, where instead of taking the union of two sets, we are taking the union of three sets, A, B and C? Could we express the number of elements in A union B union C in terms of the number of elements in the individual sets A, B and C and various intersections of these sets? So notice here that the union was expressed exclusively in terms of the individual sets and intersections. There were no unions on the right hand side. Similarly, can we express this union purely in terms of the individual sets and their mutual intersections? So let's look at a couple of ways of deriving a formula for the number of elements in A union B union C. In the first method, what I'll do is I will treat A union B as a larger set called D, and the reason for doing that is we can eliminate two of these names and replace them with one name. So the result will be the number of elements in D union C. We already know how to calculate the number of elements in D union C. We can use this formula, and by replacing the number of elements in D union C with the right hand side derived from this formula, we can then replace back A union B in place of D and then further open up the right hand side. So let's try that strategy. We have here the number of elements in D union C because we have made D equal to A union B. Now this value is nothing but the number of elements in D plus the number of elements in C minus the number of elements in D intersection C. Now we can replace back A union B in place of D. So the first term can be written as the number of elements in A union B plus the number of elements in C minus the number of elements in A union B intersection C. Recall that when you have a union and an intersection in the same expression, it's important to parenthesize the expression to indicate which operation is being done first. Since we are assuming here that we have the set D, we're going to replace D with A union B with parentheses around it. Now our goal is to have on the right hand side for this expression purely the sets themselves and their mutual intersections. We don't want any unions on the right hand side. So let's first try to eliminate this union. We can do that by applying the same formula. The number of elements in A union B is the number of elements in A plus the number of elements in B minus the number of elements in A intersection B, and we can write the remaining terms as they are. So we have A, B and A intersection B now and C here. We still have a union over here which we need to eliminate. So let's do that. Let's first rearrange these four terms by bringing together the individual sets A, B and C minus the number of elements in A intersection B minus. Now how do we go about eliminating this union? Well, we could use the associative law, and in preparation for that we can first use the commutative law so that we have C appear before A union B. It doesn't matter whether we express this as this intersected with this set or this set intersected with this set. So we can rewrite this as C intersected with A union B. We are just applying the commutative law here by exchanging the operands. That doesn't make any difference to the result of the intersection. Now this is in a form where we can use the distributive law. So let's do that. C intersected with A union B can be written as C intersected with A union C intersected with B. We can actually eliminate this bracket for now because we don't need it here. So this set C intersected with A union B is just being written as C intersected with A union C intersected with B. So now we have this set and this set being unioned. So if we call this set as S1, we call this set as S2. Now we can eliminate this union operation by using the same formula. So this would be the number of elements in S1 union S2, which can be written as the number of elements in S1 plus the number of elements in S2 minus the number of elements in S1 intersected with S2. These terms won't change. Now we're going to replace this term, the number of elements in S1 union S2, with the number of elements in S1. S1 is the set C intersected with A, plus the number of elements in S2, which is C intersected with B, minus the number of elements in S1 intersected with S2. So what is S1 intersected with S2? S1 is C intersected with A, and if we take the intersection of that with C intersected with B, we have a sequence of 3 intersection operations now, and it doesn't really matter how we parenthesize it because we have the commutative laws and associative laws applying for a sequence of intersection operations. We can do them in any order we like, rearrange the operands if necessary. So we could have C intersected with C appear first, and then we could take the result of that and then intersect it with A and then with B. C intersected with C is just C. So we would effectively be taking the intersection of all 3 of these sets, A, B and C. So this is what we would get. So now we can open this bracket. Let me first write this term. This is minus the number of elements in C intersected with B, which I can write as B intersection C. Then let me write this term, minus the number of elements in C intersection A. This minus and this minus make it plus. The last term would be number of elements in A intersection B intersection C. So now we have an expression for the number of elements in A union B union C exclusively in terms of the individual sets A, B and C and their mutual intersections.